the topic assigned to me is Hohenberg-Kohn Theorems. But that would come towards the end of my lecture. I'll have to prepare the background first. And I'll bring in many different, topics during my lecture. So, first of all, let me tell you, this workshop is about density functional theory. So, you can just simply dissect all the terms, density, functional, and theory. I will try to give you certain glimpses of these things. What exactly do we mean by density? Here, Manoj has started in his unique style. I will tell you also something. What is a functional? He has already introduced you to Thomas Fermi functional. And what is the whole theory is about where we use density functionals. In fact, it's a type of quantum mechanics where density is the basic variable. In the place of, let's say, many particle wave function, or even, let's say, single particle or two particle density matrices, we are using a simple scalar three-dimensional function. Nothing else. Even for a many electron system, it's a three-dimensional function. Okay. Now we have to know what exactly do we mean by a functional, and then how we can make use of density. First of all, we have to know why at all we are after density, and then whether we have, say, excuse me. Say, legitimate reasons to use density in the place of many particle wave function. The question is whether a three-dimensional function of three variables, can substitute a function of three n variables, where n is the number of electrons. So we'll develop gradually, and so we have to go back and forth between the two worlds, the wave function based common, say, quantum mechanics versus density based mechanics like density functional theory, and what will allow us to go back and forth. So we have to develop that theory mathematically, rigorously. So first we will start from the wave function picture. Here, majority of the students are from chemistry background. Okay, so we'll start from, let's say, many electron, say, or polyatomic molecule where there are several electrons. Okay, so you have a molecule. Say you, and these are the nuclei. Okay, if you want certain bonds also, let's say, and there is some electron density distribution. So this is generally the way we look into the molecule. Now, in this case, there are two important aspects you can see. One, the positions of the nuclei. And the positions of the nuclei will determine what we call the geometry of the molecule or the molecular structure. In addition to that, say, these structures, say, they are changing because the nuclear positions are changing. What are the nuclear, say, degrees of freedom will give? Like translation, rotation, vibration, they are changing the nuclear positions, and that will change the geometry. When it changes the geometry, the electrons, what the electrons are doing, they will readjust themselves so that they will try to minimize the energy of the system or it can be better understood in terms of the forces. At any given such position, you have nuclear repulsion, you have electron repulsion, you have electron nuclear attraction. So the electrons will try to follow this also, and I will tell you there are two different time scales so that we can separate out nuclear motion, at least as a first approximation. Nuclear motion and the electronic motion can be treated separately. So what happens? The adjustment of the electrons are done in such a way that the resultant of all these forces, electron-nuclear attractive forces, electron-electron repulsive forces, nuclear-nuclear repulsive forces, they become zero. And you know from classical mechanics, when there is no force acting on a system, we call the system is in its equilibrium. So this particular geometry, we'll call it equilibrium geometry. Okay, I'll tell you, I'll give you a much better definition of that as we go along. And this is the geometrical structure of the molecule, which tells you where the nuclei are. Okay, and corresponding wave function, electronic wave function, will give us the idea of the electronic structure. So when we talk about the molecular structure, we are talking about two different types of structures. Remember, geometrical structure and electronic structure. So mostly we are doing electronic structure calculation at a specific nuclear geometry, and then we change the nuclear geometry and generate the whole of potential energy surface and do the electronic structure calculation. Okay. So that means, say, if I want to write, we don't consider, let's say, the electron, distribution as a smeared out charge. First, we consider them, let's say, just simple charged particles. Okay. That means we visualize the molecule as an assembly of several charged particles. Some of them are heavier, some of them are lighter. Okay. And they are undergoing their typical motions. They are moving, they have their own kinetic energy, and under, say, the action of some potential generated due to their own Coulomb repulsion and also electron nuclear attraction. And that is happening. This is a dynamical feature which is happening. And that we are trying to simulate as, let's say, the superposition of various types of simple-minded motions, which separately perhaps we can solve, like vibration, rotation, translation. Okay, these are the two paradigms. In one case, the molecule as such, if you want to see certain charged particles, they are moving under their own Coulomb field. Now, solving that problem, we may take, say, help of some simple-minded motions, and we say that if all of them are being carried out simultaneously, we can perhaps simulate that complicated picture. Okay. So in this situation, what is happening now? We have the geometrical structure and the electronic structure, I told. In order to appreciate those two separately, obviously we have to go to what is called Born-Oppenheimer approximation. Now, before that, say, if I want to think about the coordinates, let's say there are n electrons and m nuclei. So I will write a vector R is like x1, y1, z1 up to xn, yn, zn. And similarly, this vector R is something like x1, y1, z1 up to xm, ym, zm. So in this vectorial notation, so these column vectors, they are taking care of the coordinates, individual sets of coordinates of the electrons and the nuclei. Okay. So the net Hamiltonian would depend on this, and it will obey the Schrodinger equation, let's say. For a given molecule, let's say, we can write the molecular Hamiltonian, let's say minus half sum over I1 to n del r I square minus half sum over, let's say, alpha 1 to m del r alpha square. These are the kinetic energy of the electrons, kinetic energy of the nuclei. Then you have, say, plus, say, I can write sum over alpha beta less than alpha 1 by r beta minus r alpha. Of course, I can write it the way Manoj wrote, put half and then put this over there. So plus sum over I, sum over j less than I 1 by ri minus rj minus I is 1 to n, alpha is 1 to m, say z alpha here, z alpha, z beta will be there, z alpha by ri minus r alpha. Okay, so this is your kinetic energy of the electrons, kinetic energy of the nuclei. This is your nuclear repulsion. This is electron repulsion, and this is electron nuclear attraction. Okay, so this is simple molecular Hamiltonian. I'm not getting. Can you be a little bit louder?
Third term, Z alpha, Z beta will be there in the third term, not in the fourth one. And also there will be one M alpha in the second term. Mass of the nuclei has to come in the second term.
No, okay, so on M alpha, let's say like it like this. Okay. Actually, sometimes by mistake, sometimes deliberately, I'll put something over here. Remember. So I want to know whether you are hungry, whether you are awake. So you can see this is nuclear repulsion, electron repulsion, electron nuclear attraction, and so on.
So you are missing E square.
What?
That is why you are missing E square then. The repulsion term, electron repulsion.
No.
E E square by
E square, he has taken already atomic unit. So in that case, because I am using both the types of particles, that's why I put the mass. Otherwise, this mass, electronic mass also is 1. Okay, you see, I didn't put H cross square. You know, the kinetic energy operator H cross square also should have been there. That is 1. Okay. So now, in this case, what we will be doing that we assume that, let's say, there are two different time scales. Electrons, so let's say nuclei are about 2000 times heavier. So they are moving relatively sluggishly, and you have different time scales. And what happens, we can assume that as electrons are moving much faster, by the time an electron moves from one place to the other, it sees the nuclear framework more or less static. Okay, so point number 1. And by the time the nuclei, so we go to that time scale, we see the nuclear motion. Electrons must have done several such motions, and it will see some kind of average measured out electronic charge distribution. Okay, that means I can generate the typical electron nuclear attraction for the nuclear motion, also for the electronic motion. Okay, so electronic motion means one electron is seeing a static frozen nuclear framework, and during the nuclear motion, it is seeing the interaction of the nuclear charge, let's say, with some smeared out electron density distribution. So the point here is that I will freeze the nuclei. So R is frozen. So for a given R, now I will write this, that Hamiltonian, this is approximately electronic. Here I can see, instead of comma, I have put a semicolon. That means this R is now a parameter, not a variable, for the electronic Hamiltonian, plus a nuclear Hamiltonian, which exclusively depends on R, because it doesn't see any nuclear coordinate. It is new. They are all smeared out. Okay, because it's having much slower motion by the time electrons have undergone many such things. And the corresponding wave function, obviously, if the Hamiltonian is additive, wave function would be multiplicative. Okay. And we'll assume that this electronic Hamiltonian will obey what is called electronic Schrodinger equation. And that is basically the equation what we solve when we talk about the molecular electronic structure calculation. And that equation is H electronic R this is E electronic, which depends on R, because if you change the nuclear geometry, the corresponding electronic energy also will change, because the electron nuclear attraction potential enters into this. So electronic. So here, if I take this term, then I take this term, and then I take this term. These three together will give me the corresponding electronic Hamiltonian. Okay. So now, if I substitute all these into this equation, then what I get in addition, this is your electronic Schrodinger equation, electronic Schrodinger equation, and this we solve when we talk about the electronic structure calculation. And here you can see, in addition also I will tell you, so the remaining terms like nuclear kinetic energy, nuclear repulsion, if I just take this, And if you substitute this over here in this equation, what I get ultimately for the nuclear motion, so nuclear R plus NN R plus electron, this R, some psi nuclear R is E psi nuclear R. And this you can consider to be the Schrodinger equation for the nuclear motion. Okay, and this one we call, say, nuclear potential energy, because you can see that if you want to have something like Hamiltonian, this is the kinetic energy, this is the nuclear potential energy. And if you plot this as a function of the nuclear coordinates, you generate what is called the potential energy surface. Okay, and from the potential energy surface, looking at the critical points there, say the minima will correspond to reactant, product, intermediate, etc. And you can do a frequency analysis to find out if there is one imaginary frequency, you get a first order saddle point that will correspond to the transition state, and so on. So you can higher order saddles also. You can just thoroughly study the your scanning of the potential energy surface. So what are you doing basically? Freeze the nuclei, get capital R, from there get electron nuclear attraction stuff, solve the electronic Schrodinger equation, generate the electronic energy, add it to nuclear repulsion, and then solve for the nuclear motion and reiterate this. Okay, you get a new set of nuclear coordinates and then reiterate. Generally, the nuclear motion is not solved quantum mechanically. Generally, you get the force, from there you solve Newton's equation of motion and generate the new positions, nuclear positions. Okay, that will allow you to get the whole information. But here we will talk mostly about only this part. Okay, molecular electronic structure calculation for a given nuclear framework or a given geometry of the system. And as I told you, the whole methodology, when I carry out the whole operation, I know the equilibrium points so that I can calculate the electronic structure for equilibrium geometry of a molecule. Okay, or similarly, I can get the electronic structure of the transition state. Reactant, product, intermediate, whatever, I know everything is there on the potential energy surface. Perfect. We can generate the reaction mechanisms also, how from reactant to product via transition state, intermediate, the reaction proceeds, that also we can get it from this. Okay. So now, we will write this, let's say H psi as E psi, only for this one now. So I am changing So this is, let's say, the electronic Schrodinger equation, which we'll have to solve for a given nuclear framework. So that backdrop, now onwards, I am not going to tell that I am solving the electronic, say, Schrodinger equation for the electronic motion for a given geometry, given nuclear framework. Okay, you can see that I am using synonymously the nuclear geometry and molecular geometry, because when we talk about the molecular geometry, we generally consider only the positions of the nuclei. We don't bother about the electrons. Okay. And once I get the equilibrium geometry, let's say where there is no imaginary frequency and that is the global minimum structure, there for that geometry, whatever, if we write in terms of bond lengths, bond angles, we can call them as the equilibrium bond lengths and equilibrium bond angles of that molecule. Okay. So this wave function now will start from here. So first we will consider one electron situation, just only one electron. So if you have only one electron system, its wave function is just what we call an orbital. Okay, orbital is the wave function for one electron systems. So if I say that the electron is there in, let's say, orbital A, so that means A is a function of R, that's the orbital, and with, let's say, spin, in general I am writing, say, alpha S, with spin alpha. So this is what we call a spin orbital. So X is generally used here as a common coordinate, spatial variables and the spin. Okay. So this one is just a spin orbital, one particle case, remember. So this is the wave function AR into alpha S, where AR is the spatial orbital. Now, suppose I want to find out the probability of finding that electron in some volume element dx. Okay. So that probability finding the electron in dx, this would be what? Psi star x psi x dx. Okay. That means I can write it as AR mod square alpha S mod square dr ds. Okay. And this one, by notation, I will write it as rho x dx. Okay. So my rho x dx is psi star x psi x dx here, this. And now, if I don't want to have any relation to spin, like it may be alpha spin, it may be beta spin, then I can get rho r dr as, say, dr integral rho x ds. Actually, we don't do integration, we do summation, because spin is not a continuous variable. So we do actually summation. Okay. So what is this rho r? Okay. This is basically the probability density, and we call this, let's say, single particle density or the density for the time. But it's very obvious, this density is not giving us anything new, because for one particle problem, it comes automatically, isn't it? Now problem comes when we try to go for a similar description for a many electron system. So a general case, let's say. So the wave function, let's say, is x1, x2 up to xn. This is a general case wave function with spin. We know what is the spin of the first electron, second electron, and the corresponding positions of the electrons, first one, second one, etc. Now, if I ask you, what is the probability that the first electron would be in dx1, second electron would be in dx2, and remember, when I am telling dx1, that means I am also specifying the spin. dx1, this in dx2, this in dx3, and the nth electron is in dxn. So what is the probability? This is psi x1, x2, xn, psi star So this is the probability of finding electron 1 in dx1, electron 2 in dx2, and up to electron n in dxn. Okay. Now, let's say I am reducing the dimensionality of the problem. I am telling you find out the probability of getting electron 1 in dx1 and forget about all other electrons, they may be anywhere. Okay. So, electron 1 in dx1 and rest of the electrons anywhere. That probability would be integral okay. Other electrons we have integrated out, they may be anywhere else. We are not specifying their, say, positions and the spin. Only we are interested in electron 1. Okay. And this one may be say this is giving me that probability of only one particle is this. Okay. Now, you see, if I tell electrons are indistinguishable, I don't know which one is electron 1, which one is electron 2. So, I get this type of integral for electron 1, similarly for electron 2, similarly for electron 3, and this definition is symmetric with the electron coordinates. That means, if I want to say any one of those electrons in dx1, that if I write it as rho x dx, this would be n times rho x1 dx1, isn't it? Any one of those electrons can have the same. So altogether, if I want to tell that any one electron would be in some volume element dx, it would be n times this one. Okay, this was exclusively for electron 1. Now, similarly for electron 2, you will get a similar picture. Electron 3, n times you will get this.
Why is this same logic not followed in the first question? For example, if we say that first of all, I would like to clarify which of the languages is correct. For example, could we say do we say electron 1 in dx1, electron 2 in dx2, and so on, or say 1 electron in dx1, 1 electron in dx2, and so on? Which of these should be the correct language?
You see, there is no incorrect language over here. I am telling you I want to calculate a particular probability density and I am giving the expression. So nothing is incorrect, nothing is correct over there. This one is written for a specific definition. This is also written in a specific definition. So I am trying to derive something which we call the density. You follow the logic only, nothing else. Okay. So if I tell at the very beginning that consider all electrons are indistinguishable, it would be totally jumbled up, you will not understand anything. Okay. If you are clever enough, you just bypass this step. You go straight away to this, no problem. But you will understand better if I gradually develop. So now you understand this one. After this, if I tell that I don't bother about the spin also of those electrons, then what I will be doing, that this rho x ds integral, where you have this n, rho x ds integral, this one I will call rho of r. Okay. So now what we are trying to do, we want to find out the probability of any electron in dr, any one of the electrons in dr, without referring to its spin. That is given by this rho r. Okay, actually this is, as I told you, sum over S rho x. So this quantity is this one. Okay, it is not the integral because ds is not a continuous function. Okay. So once again, let me tell you what exactly is this rho r. Rho r is the probability of getting an electron in an n electron system without referring to its spin in a volume element dr is rho r dr. Okay, so this rho r gives you the probability density. Okay, so probability density of having any one of those n electrons in some volume element dr is given by rho r. So let's go back. What is this rho r now? So rho r is n integral psi x1 x2 xn psi star x1 x2 xn dx2 to dxn, and in addition you have ds1. Is it okay? That is your rho r. You see, follow the steps. Now do you have any question? I have defined something here. For a specific probability, this is now the probability density, and that probability density is defined in this fashion. So what is this probability density basically? It is the probability density for finding out an electron with any spin of an n electron system in a volume element dr. Is it clear to everyone? Yes or not? You have any n electron system, atom, molecule or whatever, you want to find out in a given region of space, what is the probability that you can find out an electron? Okay, that's the probability density in that. Okay. So, what you can see that this particular quantity is the so-called density in DFT. The very first letter of DFT is D. If someone asks you what is that density, this is the density. Okay. So if you don't know the density, then doing DFT is meaningless. You have to know what exactly do we mean by this word density. Okay. Now suppose if I want to say dx2 to dxn is ds1 because the first electron also, it's irrespective of the spin I am doing. That's why it is on ds1. And you can see now, if I do this, rho r dr would be n. So that means now this dr is your dr1. Okay. So that will take care of everything. This n will be there. This is what is called normalization constant. Remember, Manoj wrote this. Rho r dr is integration is n. Okay. Do you follow? So, like out of this dx or dx1, first I have taken integration over ds1, and then if I do it with dr, only everything will be 1 because wave function is normalized. Okay. So, your rho r dr integral becomes n. And this is what we call normalization condition of the density. Okay. So now, if I ask you, what exactly do you mean by density? Any one of you, can you tell before I proceed further? Any one of you? You tell, otherwise I will not proceed. Tell. What is density? Be louder. We are talking about many electron system. We are trying to write it in a single electron language. But our system is many electron system. Remember, n is there. So what is density? Single atom. You didn't understand anything. Where is the atom coming into the picture? I told it's a many electron system. It may be many electron atom, it may be many electron molecule, whatever. Isn't it? There are n number of electrons in your system. Okay. So what do you mean by density of that system? So density is the probability density of getting any one of the electrons without spin in a given volume element. Okay. Per unit volume element is the probability density rho of r. That is the density what we use in DFT. Once again, tell. I have told it maybe 10 times. At least one of you tell once. What is density? What happened? You have to tell everything. Probability of finding an electron of an n electron system, okay, in a given volume element per unit volume element, that probability density is called the density. Okay. So you now know what is the density. Without knowing this, you cannot proceed further. Now, when we talk about, let's say, we want to calculate, let's say, the probability of having one electron in, let's say, dr1, another electron in dr2. So this density we call density, or this is also called single particle density. Okay, because we are talking about only one electron. But suppose if I tell you that one electron is in dr1, another electron is in dr2, without referring to its spin or their spin, what is the, say, joint probability that now I am taking out two electrons from n, one electron is in 1, another electron is in 2. What is the probability? That one is called a two particle density. So this one I called you density, the common language for the single particle density. Okay. So now we are bringing in, say, that rho of R is single particle density. Now I am talking about two particle density. This is rho R1, R2, let's say, if I write two particle density. I will derive exactly the same way. Instead of integrating from dx2 to dxn, I will integrate dx3 to dxn. And remember, if the first integral can be obtained in n different ways, then that can be obtained for the second electron in n minus 1 different ways, because the first one is already occupied. That means it would be n into n minus 1 integral psi x1 to xn psi star x1 to xn, then dx3 to dxn, and ds1 ds2. Okay, this n into n minus 1. So this gives you the probability density of getting electron 1 in dr1 and electron 2 in dr2. Okay, this is required. You remember we had talked about some Hartree potential. You are bringing in two different densities. This actually, if you want to write in terms of this two particle density, you will get it. So how will you make use of this density in calculating, let's say, the physical quantities now? And then we will show you the inadequacy of this method, so that we have to bring at least something where from the DFT will come into the picture. So suppose once I know the wave function, how do I calculate any physical property? It is just the expectation value of the corresponding operator over that wave function, isn't it? That means if I want to calculate some property f, expectation value would be your psi f, this one. So let me now go back. You remember for electronic Hamiltonian, you had kinetic energy operator plus electron nuclear attraction plus electron-electron repulsion. Okay. And this one, you remember, Manoj has talked about this as V external. You told V external, this one. Or sometimes we don't write this word external, small v as a function of r. This is what we call the external potential to the electron. Why external potential? Because electrons, they don't have the information where the nuclei are. So you have to supply that information. In fact, it is so robust. In addition to this, if you place the atom or the molecule in external electric, magnetic field, etc., you can add them also along with this electron nuclear, that external potential. Okay. So you can see this is a multiplicative operator. This is also a multiplicative operator. We will see the nature of this. But this one is a differential operator. So if I want to calculate or let's say find out the electronic energy, what I have to do, if I know the wave function, I have to calculate this one, expectation value of the Hamiltonian, electronic Hamiltonian operator over the corresponding wave function. Now, the first thing, if it is, let's say, one particle, multiplicative operator. Okay. If it is one particle multiplicative operator, then what I can do, if I just put that, let's say the V of r over here, I can take this psi star to this side. This is the multiplicative operator. Try to understand this. I can take it towards that side. If I take it towards that side, and remember it's a one particle multiplicative operator, so all other particles I can integrate with this integration over n particle coordinates. So that will give me what? The density, isn't it? And that along with this new normalization, this n will cancel and I will get the density. Because ultimately what I get, this is my V of r rho of r dr. It was also used by Manoj, remember. So this is your external potential. The corresponding energy component is Vr rho r dr. For writing this, you remember, I have taken away all those other coordinates, the wave function picture is not there anymore. Everything is written in terms of that single particle density. But still, my system is n particle system. I have written it first in terms of the n particle wave function with 3n variables. But once I calculate this expectation value, I can reduce it to the corresponding So this is what we will call a density functional. You remember he talked about Thomas Fermi functional, energy functional, kinetic energy functional. I will tell you in a moment what exactly do we mean by functional. And in fact, I will show you another approach for the derivation of Thomas Fermi like equation, what he has done through application of the Euler's variational principle. So, you get this. For this two particle problem, I can write this as G12 rho 1 to dr1 dr2 with maybe some half factor. This is your electron repulsion, and this is your two particle density. So you can see that still I am using the density to find out the expectation value of a two body operator. For atoms and molecules like this type of Coulombic systems, we don't get any other interaction other than the two body, maximum two body interaction. Okay, one body interaction and two body interactions. So, in principle, your density or the so-called single particle density and two particle density, they are sufficient. But the problem comes where? This one. And there comes the beauty of the density functional theory, like Thomas Fermi functional. Totally, we are bypassing this type of differential operators or other which are non-multiplicative operators. Okay. So, how do you bypass these non-multiplicative operators? So, that is the way how it is done. Suppose if I want to get the Laplacian operator, you have so minus half del square is your kinetic energy operator. So, if you want to find out the Laplacian operator, let's say the expectation value. So, this expectation value, I will write it as, say, integral psi, say, star x1, x2, xn, let's say del, if I say I am doing only, I am writing sum over del I square, I am taking only one, let's say del 1 or del I, whatever square. I want to find out the expectation value of that Laplacian. Then you have psi x1, x2 up to xn and dx1 to dxn. I am not writing the denominator. Okay, that will be a constant, just normalization. Here the problem is, now you cannot take it towards that side. Okay, and you cannot reduce it to density. It's not possible. So, what is the trick? The trick is that you tell that I rename this one. So, for which it is there, I will rename this. And then I will take it towards that side. If I take it towards that side, now there is no trouble because this is on x1. So, anyway, it will not operate on x1 prime. Okay. Then I do the whole operation, whatever I did before. After doing the operation, I will tell no, my x1 prime is same as x1. Okay. That means I will generate a quantity, say psi star x1 prime x2 xn psi x1 x2 xn dx2 dxn, and of course your n factor also will be there, and integration over dx2 to dxn. You remember? So now what I am doing? I am doing exactly as if it is a multiplicative factor. I have taken the bra function towards this side. I have changed the variable x1 to x1 prime so that it cannot operate on this. I define this quantity, and before integration, I will put x1 prime equal to x1. Okay. So this quantity is called single particle density matrix. Now you can see it is no longer a density function. It's a single particle density matrix, because here x1 prime and x1, they are different variables. So we rewrite that expectation value in terms of single particle density matrix, and before the final integration, you say x1 prime equal to x1. Obviously, similarly, we can define a two particle density matrix. There you have n into n minus 1, here x1 prime, x2 prime, and rest dx3 to dxn, and here it should be n into n minus 1. That will give me a two particle density matrix. And you see that the, say, diagonal elements of this density matrix is nothing but your old densities, isn't it? So if I write, say, rho x1 prime x1, if I write rho x1 x1, that is nothing but rho x1. Okay. So diagonal elements are just the densities. Now, in DFT, we will tell that we want everything in terms of density, not even density matrices. Of course, density matrix is a much simpler version of the many particle wave function, but still we don't want that. We want everything in terms of the density, that simple three-dimensional function density. Okay. In density functional theory, actually, we want to see that everything can be obtained in terms of densities. We will see that actually we will obtain them as density functionals. Okay. So now we have to know, we have learned density, single particle, two particle density, single particle density matrix, two particle density matrix, that we have already learned. And our main aim, of course, to write everything in terms of rho of R. That is the single particle density, which we call the density. Perfect? Now, so now you can see that I am basically telling you something about the ABC of DFT. What is D, what is F, what is T? This is my lecture today. D part is over. Hopefully, I have explained what is D. Okay? Now, what is a functional? Actually, first of all, let me ask you, what is a function for a curve? So, you have a set of numbers, let's say x1, x2, xn, if I write y is f of x, so it will map into another set of numbers y1, y2, yn. So what it says that in a given function, for any say value of the argument, I get a number. So this is one set of numbers to another set of numbers. This is a map. That's my function. Now if I tell that I want to find out a correspondence where a set of functions is corresponding to another set of numbers. I am telling not these numbers, say a function called y1 of x, another function y2 of x, let's say yn of x. Say, a function belonging to a specific class, if I have a correspondence which can map it to a set of numbers, then that map is called a functional. Okay. Like suppose if I talk about a functional, say f of y is, let's say a to b x to the power n dx. It's a definite integral. So I will get numbers. If I put first as dx, then x dx, x squared dx, x cubed dx, each one will give me one number. So a set of functions is mapped to a set of numbers. Okay, this is called a functional. So you can say this is not a function of a function. Many highly educated people, they say, what is a functional? It's just a function of a function. No, it's not a function of a function. So if I say my fx is e to the power sine x, it's a function of a function. But it is not a functional. Because it's a function, it's not a number. Okay? So let me write a functional, let's say j of y is some integral a to b f x y y prime dx. So I have a simple function of y is a function of x, y prime is the first derivative. So I want to define something where you have a continuous first derivatives in a given domain a to b, and let's say I know that y of at a and y of at b, these are known. So I get all possible such functions. I change the function, only that I have to know that they will have these values. Of course, I can just simply normalize and get those values, and the functions must be having a continuous first derivative in that, so that I can define this class of properties, and this is a number. Remember, this is a definite integral, so this quantity is a number. I change the function here. If I change x, I cannot change this, because remember, I am integrating over x. It's a dummy variable. If I want to get a different number, I have to change y, not the x. Okay? So I go for a class of functions y of x. They are known in the boundaries and they have continuous first derivative. So I can define this particular quantity, which is an example of a functional. Which one?
Definition of functional. Is it necessary that they satisfy the same?
If you want to compare the numbers, otherwise you cannot compare the numbers. These numbers, if you want to compare, you have to have it. Say suppose if you want to find out the minimization of some GAY, brute force method, you have some series of numbers, which one is the least value? And that's simply, you find out the factor, it's arithmetic.
As you said, boundary conditions have to be
Yes.
Makes sense.
If you don't want to compare anywhere, then no problem. You are getting some number, that itself is sufficient. But if you want to compare those numbers, then you have to have the same footing. Now, in this case, y prime is your dy by dx. You see, when you do the variational calculation, standard, let's say, electronic structure, you do the variational calculation. There, remember that we define this quantity for your. Do you remember this? Then you optimize the parameters present in your trial function and minimize this energy. That's the variational calculation. This is a functional. You see, because this energy is a number and that number changes with the trial functions. So this is just, you know what is a functional. We'll go to a point in density functional theory that we are interested in density functionals. That means there different types of densities will appear as this y, and what are the values of those functionals, that should be our concern. Now, before I prove that it contains that information, we have to know why are we so interested in density. We know wave function theory, it is well developed, everything is known, but why to go for some shortcut using density, bypassing wave function? First, you can compare it some experimentally obtained quantity. Do crystallography. You can get the crystallographic data, we can compare with this experiment. Second, Manoj has touched upon this. We live and perceive in a three-dimensional classical world. We cannot, even four dimension, we cannot just apprehend, we can have some idea about a four-dimensional stuff. Forget about 3n dimensional stuff. Even for simple neon atom, wave function is 30-dimensional. Forget about molecule like DNA or other. So what will you do with that wave function? So if you want to touch upon that function, this is your density function, which you cannot do with the wave function. Now, if you know a function in a three-dimensional space, you can build models. Chemists are fond of going for the models, which you can do using density. You, in a much rigorous sense, not arbitrary ad hoc ways of getting the models as it is done in chemistry. The most important part of using density is the drastic reduction in computational labor. You are doing everything in a three-dimensional space. And not only that, no large molecule, I am telling it with a guarantee, can be touched upon using any standard wave function based theory. Only savior is any density based theory, like DFT. You will hear many forms of DFT and so on. So, but today I am not going to touch upon anything on the actual ways of implementing electronic structure methods. The most famous, of course, is the orbital based method. That's an approximation, as he has already told, which is called Kohn-Sham formalism. I think Professor Sen will tell in detail. I will not touch upon that. What I will tell, on the other hand, everything in terms of density. And as he has already mentioned, that you can consider this is a kind of basic theory of even orbital free DFT, what is also famous these days. So what will you do? Your first job is to talk about, so this is the functional you have. And I told you that this functional, I first assume that any physical property can be considered to be a density functional. Okay. Now, if it is so, we should have some roadmap. How to write those functionals is a different issue, but how to get that density. Obviously, whatever algebra I did so far, I don't want to do that to get the density. Like if I tell you that you get the many body wave function, get psi star psi, do integration, multiply by n, no. Then anyone can ask that if you have already the many particle wave function, why to go for the density? Why do you bring in another variable? You do expectation value over those many particle wave functions. So the main aim, now you have two-pronged problems. One, you have to prove that density contains all information so that you can substitute, you can replace the wave function, many particle wave function by density, which is just three-dimensional function for even a many electron system. Second, how to get that density. How to write a functional is a different issue, but how to get the density? Obviously, we don't want to get the density from the wave function. This is our first aim. Okay. So for doing this, obviously the question will come that we have to somehow get, let's say, energy density functional. So energy written in the form of a density functional, and I have to find out a minimization procedure of that energy. So that I want to go for a variational approach. Okay. So now I am giving a slightly different route than what Manoj has already told you, a linear variation like rho plus grad rho. I am going in a slightly different route, applying calculus of variations. I may take a little bit more time. So, no, more than 15. Yeah. So, we'll talk about calculus of variations. So, Euler's theorem. Now, before going into Euler's theorem, let me define something called a functional derivative, or this is also called variational derivative. Okay, this is what is called a functional derivative. That means now I am varying a functional by varying the function. Remember, it is different from your ordinary derivative, dy dx. Okay, this is a functional derivative, and this variation is called the functional variation. Instead of writing d, we put it like this, delta. This is a functional derivative. Okay. So this is, you remember, what is the functional? J of y is a to b f x y y prime dx. Okay. So you take the derivative of f with respect to y minus ddx of f with respect to dy dx. Again, joint exercise to you, where he did rho plus grad rho and defined the Thomas-Fermi equation. You do this. Your original functional is Thomas-Fermi functional. You do this and find out the Thomas-Fermi. Do this means you apply Euler's theorem. Okay. It's just 2-3 lines, but you can derive what he did. So what is Euler's theorem? You remember, in ordinary derivative, you know the necessary condition to have an extremum of a function. The first derivative must be 0, and second derivative, whether it is positive or negative, it gives you a sufficient condition. Although there is a necessary condition in calculus of variation, there is no sufficient condition. You cannot tell with certainty that there exists something like this, which you can do in ordinary calculus. Okay. So in this case, what is the necessary condition? The Euler's theorem tells that the necessary condition for any functional j of y, for a given function y, to say the j of y to have an extremal value is its functional derivative should be 0. Do you understand? That means you want to tell del y should be 0 is a necessary condition for j of y to have an extremum for a given y. Okay. So suppose if I tell this is my Thomas-Fermi energy functional, this rho is y is the rho, then I can immediately put this and put this equal to 0. That should give me Thomas-Fermi equation. That's minimum energy. Okay. You try 2 lines, you get Manoj's result. Not now, because otherwise you will miss your lines. So then we have to talk about constraint variation. Remember, he also told another thing, that the densities must satisfy the normalization condition. So rho r dr must be n. Okay. So what you write basically in this case, del. So first you can see that this would give me del E rho is mu, where mu is the Lagrange multiplier associated with the normalization constraint. Where from I am getting it? Delta E rho minus mu, let's say integral rho dr minus n, this should be 0. What it says that I am taking the derivative, this Euler condition gives me that the functional derivative is 0. And in addition, I have a condition. This is constraint variation, that I will take only those densities which will minimize the energy. At the same time, it would be normalized. And this is what is called Lagrange undetermined multiplier. Okay. And this mu Later on, you can see, say maybe tomorrow itself, when I go to conceptual DFT, I will tell you that it is identified as the chemical potential, which has something else to do in chemistry. But it is coming straight away from the normalization condition of the density. It is the Lagrange multiplier. Okay. So, if I write energy E rho as T rho plus V E rho plus integral rho r Vr dr. You remember this is your electronuclear attraction, this is electron-electron repulsion, the kinetic energy. Then what you get, and this together is called FHK rho. It is universal because it doesn't depend on the external potential. This is called universal Hohenberg-Kohn functional. Okay, Hohenberg-Kohn density functional. So if I put it over here, what do you get? Vr plus del FHK rho del rho is mu. So you can see this is an equation which is called Euler-Lagrange equation. Why? Because ordinary Euler condition plus Lagrange multiplier to take care of the normalization constant. Okay, this is Euler-Lagrange equation, which is your deterministic equation for the density. If you get some approximate form for Hohenberg-Kohn functional, which we can then say you have Hartree functional, exchange correlation functional, whatever, you just write several terms in FHK rho. Ultimately, you get this is simply an equation in density itself. You have no wave function, no density matrix, nowhere. So you can solve this equation now to get the density. Okay. So our starting point was to get the density from somewhere. You can see the Euler-Lagrange equation gives me that. Now in this T rho, if I put say non-interacting kinetic energy, that means sum over minus half del I square, and dump all ignorance. Here you have a Hartree potential, whatever quantum part of the electron-electron repulsion, dump that. Non-interacting part, kinetic energy interacting portion, dump into that, call it exchange correlation potential. Okay, that is what is called Kohn-Sham theory, because you are now writing minus half del I square for individual orbitals. You transform this Euler-Lagrange equation, which was in terms of density, to Kohn-Sham orbitals. Okay. Huh? What?
You still have to prove that I can use the density.
Yes. So Manoj is hungry. I'll finish. Maybe extra 5 minutes I will take. No. So the question is, whatever I have done so far, I assume that the density contains all information. So you can see the Hamiltonian is completely characterized by two quantities, N and Vr. If you remember the Hamiltonian, the way it was written, if I have to write minus half del I square sum over I equal to 1 to N, I have to know the number of electrons to specify that, and external potential I have to specify. Rest everything depends on density or other. I don't need anything else. N and Vr will tell me completely, it contains the all information about the system. Now the question is, if I know the density, Getting n is a trivial job because if I know the density, I simply integrate, I will get. So this is, I am going towards Hohenberg-Kohn theorems. So if I can get somehow the information about the external potential from the density. Remember, external potential has nothing to do with density. It is coming from the nuclear positions. So if I get that information from the density, then knowing Hamiltonian, in principle, I know the wave function. Knowing wave function, in principle, I know all properties. Because from here, I know psi. From psi, I know all properties. In anyway, I am getting, my question is now that V of R and N, of course, Schrodinger equation so it is the inverse map. If I know N and VR, I know Hamiltonian, I know the wave function, from wave function, I know the definition of the density, I can generate the density using Schrodinger equation. I have to solve to get the wave function and then the density. So Schrodinger equation maps N VR to rho. What I have to do from rho, N I can get simple quadrature, but I have to get V. So I have to prove that rho contains all information about the V. And that is your DFT. So what it does, so I have to talk about two theorems given by Hohenberg and Kohn. The first one tells you that the V can be obtained from density except perhaps with some additive scalar constant. So this is the first Hohenberg-Kohn theorem that V is obtainable within a trivial constant from the density. So Hohenberg and Kohn, they started their proof, which is called reductio ad absurdum. What it says that you start with certain supposition and logically derive a condition which contradicts the first one, and that tells you that it is not possible, so our supposition was wrong. So what is their supposition in the Hohenberg and Kohn theorem number 1? That VR is obtainable from density with maybe trivial additive constant. So what they started, they considered that let's say there are two different external potentials, VR and V prime, V tilde R, let's say. And both of them will give you the same density. Okay? Now, what they say that for the VR, let's say it corresponds to Hamiltonian H of R, and that corresponds to psi of R. And V tilde R corresponds to Hamiltonian tilde R, and that corresponds to psi tilde R. But both of them will give you the same density. That is my supposition. That two different external potentials differing by more than a constant can give the same density. Can give the same density means from this, if I construct the Hamiltonian, then solve the equation, get the wave function, define the density out of it, and do this, and you will get it. Okay. So what it does, that let's say the energy corresponding to this is E0 and energy corresponding to this is E0 prime. So if you know the Hamiltonian, if you know the wave function, so in Schrodinger equation also you get the energy values. Okay, so we have started actually with the Hohenberg-Kohn first theorem that says that external potential can be obtained within a trivial additive constant from the density. And if the density can give you the external potential, you know the density can give you the number of electrons also. So that means density gives you the number of electrons, and density, if it can give also the external potential. So that was Hohenberg-Kohn theorem that it gives. So maybe not exact here, maybe in addition there is some constant. If this is possible, that means rho r gives you n and Vr, and n and Vr can fix the Hamiltonian. So it means that rho r gives you the Hamiltonian, and if it gives you Hamiltonian, it gives the wave function, and that means it gives all properties. So if you can prove this, you will prove that density contains all information, at least for the ground state. Okay, originally it was proven for the non-degenerate situation. Later on, Mel-Levy extended it to the degenerate cases also. But excited states, there are many different things, and I think so many others will also talk about the excited states. It's not very clear that whether you can straightaway extend the Hohenberg-Kohn theorem to any arbitrary excited state. We are talking mostly about the ground state. Okay. For this, you have to know that you can invert the map. So your DFT, as I told you, that N and Vr together they give the Hamiltonian, and from the Hamiltonian, if you solve the Schrodinger equation, you get the wave function, and wave function gives you the density. That means this is a map. Schrodinger equation is the map which from number of electrons and the external potential, it can generate the density. DFT is the inverted map. So if you can get N and Vr from the density, then that is your density functional theory. As I told you that N comes automatically through a simple quadrature. So you have to prove that density contains the information about the external potential. And as I told you that the proof was reductio ad absurdum. So he wanted to prove it starting with certain supposition, and later on which lands into absurdity. That means your supposition is wrong. So what it does, say you assume that you have two potentials, external potentials, which are not more than different from an additive constant. Now this VR, let's say we are talking about two different systems. Just let me tell you, how do you define any quantum mechanical system? What is the only information you know about a quantum mechanical system? Can you tell? If I tell you, let's say you're talking about water molecule. Which information do you know about water molecule? Do you know? You know only the Hamiltonian. Okay, if you are lucky, you can solve Schrodinger equation to get the wave function, then other properties. But only thing what you know which characterizes the system is your Hamiltonian. And now you have seen the Hamiltonian is also known if you know the number of electrons for many electron system and the external potential. Okay, so we know the number of electrons, external potential gives me the Hamiltonian, and that in principle, if you can solve the Schrodinger equation, gives me the wave function. Another external potential gives you another Hamiltonian and another wave function. But our starting point is that we assume that both the external potentials are connected to the same density. Okay, so density is same, the external potentials are different. That means Hamiltonians are different, wave functions are different, but the density is same. Okay. So let's say for this problem, if I can solve the Schrodinger equation, I get the ground state energy E0, and for this problem it is E0 tilde. Okay. Now what they did, Hohenberg and Kohn, that you consider this problem and treat this as a trial function. And then you consider this problem, treat this as the trial function. Okay. So from simple variational principle, we can write E0 is less than psi tilde H psi tilde, because E0 is psi H psi. Okay. So if I put the trial function from the simple variational principle, we know that this energy must be greater than or at most equal to E0. Now here, if I just simply write this as, let's say, psi tilde H tilde psi tilde plus okay. If you add this, you will get this. But this one is what? It is your E0 tilde. Okay. Plus this one, the psi tilde gives you the same density. Remember, density is same for both psi problem and psi tilde problem. That was our supposition. And here only difference is in the external potential. So this quantity is just rho r Vr minus V tilde r dr. Okay. Because this psi tilde, again, as I told you, this is a multiplicative operator, so I can take it there, write it in terms of density. Okay, one particle multiplicative operator that we have already seen. Now, we'll start from this problem. Now, I will write this as the trial function for this. So, can you very quickly write down the corresponding expression? The same problem now I am doing, where I start from E0 tilde, that means I am talking about H tilde problem, where psi is my trial function. So, what expression do you get? Can you get very quickly? Exactly the same way you do it. So, you will get E0 tilde is less than E0 plus rho r V tilde r minus Vr dr. So, let us say this is number 2, this is number 1. Okay, are you getting that? Simply we have just reversed the conditions. Okay. If you add 1 and 2, what do you get? If you add 1 plus 2, you get E0 plus okay. So, this absurd situation, okay. So, your original supposition reduced to some absurdity. That means your original supposition was wrong. What is the original supposition? That two different external potential differing by more than a constant, they are giving the same density. So, what it says that if your potentials are different, densities must be different. You cannot have the same density from two different potentials. That means density potential map is unique. Okay. So a density potential map is unique, and one density can give you only one external potential. It cannot give more than one external potential. So if that density give you only one external potential, then it will give you one Hamiltonian, only one wave function, and that means only one set of properties. So the density contains all information about the system. Okay. But the question here is, that's why otherwise people would have told that, okay, Hohenberg and Kohn, they have proven everything, the problem is solved. No. The second theorem also I will tell, they are existence theorem. They tell that all the properties, they can be written as functionals of density, but Hohenberg and Kohn, they did not specify the actual functional forms. Okay. So that means the functional forms are not known. Okay. That you have to know, and that's why there are, say, several different zoos of functionals, and some are giving some properties better, some are giving some other properties are better, although it is known that in principle you have a functional for all properties as the density function. So this is theorem 1. Theorem 2 tells that suppose if you have a trial density, okay, now we are changing the gear. If you have a trial density, let's say I call it rho tilde r is the trial density. We will consider they are n representable densities. N representable densities means we can map this density to some antisymmetric wave function. But there are certain conditions, necessary and sufficient conditions, that if it is greater than or equal to 0 everywhere, and if it integrates to the number of electrons, then automatically it would be n representable. So you can choose from your initial trial densities, all of them. Now for a given such density, you will get, let's say, the external potential according to the first theorem, and then you get the Hamiltonian, and also you get the wave function. Okay. So if I just write this, that actual ground state density is E0. Now from the variational principle, we can tell that this must be less than EV rho tilde. Because the variational principle tells you that if your actual system is this for the V problem, then rho tilde is a trial density, the corresponding energy would be always upper bound to the exact energy. So the second Hohenberg-Kohn theorem tells you that if you have any trial density to test, it would give you some energy which would be always greater than or equal to the exact ground state density. That means it is providing you with some kind of variational recipe for obtaining the density. And that we have already seen that if you want to minimize a functional, so the standard variational procedure as we do in case of wave function based theories, we can do the same thing over here, and we can construct the corresponding energy functional with the trial density, minimize that with the constraint that the density what we have started with must be normalized. Then you get the standard Euler-Lagrange equation del EV rho tilde del rho tilde. This is, so you can solve this equation now. And for this EV rho tilde, you can now apply any known forms. It may be a Thomas Fermi, it may be Kohn-Sham, it may be whatever. Ultimately, you get a kind of equation. You have various exchange correlation functionals, various kinetic energy functionals, etc. Ultimately, you can solve this equation to get the density applying the variational principle, which is the second Hohenberg-Kohn theorem in DFT, which they have proven making use of the standard variational procedure, what you have learned from the wave function based approach. Okay. So these are the two Hohenberg-Kohn theorems. We have shown how they had proven this. Okay.